In the previous module, we have learned about the frequencies for the continuous time signals and the discrete time signals. We have seen subtle differences between the frequencies of continuous time and discrete time signals. The main difference that we have seen was that the discrete time frequency, that is small f, is having the upper cap of half or 0.5. This restriction was not there in case of the frequency of a continuous time signal, that is capital F. The capital F can vary all the way from minus infinite to infinite, whereas the small f, although it can take any value between minus 0.5 to 0.5, the upper cap here is fixed at 0.5. Due to this, all the frequencies that exceeds 0.5 are getting mapped back between minus 0.5 to 0.5, and we have seen that the 0.5 frequency, that is small f equal to 0.5, is acting as a pivotal point, after which the frequencies are getting remapped. So this illustration or graph shows a remapping of frequencies, the frequency that actually is being inferred by the signal. In the continuous time case, the period is simply the inverse of the continuous time frequency, the frequency of the continuous time signals. But for the discrete time case, the small f here is a ratio of two integers. Therefore, the period is simply the denominator of the small f. We have seen that for a signal to be periodic, a discrete time signal to be periodic, this small f must be a ratio of two integers, and if we get that as a ratio of two integers, then the period is simply the denominator of the small f. Now that we have learned about the continuous time and the discrete time signals and their frequencies, let's move on to what are called as systems. Now, as I say something, as we have learned about the signals, say for example my voice signal example that we have seen in the very first lecture, my voice signal is being obtained through recording through a microphone. So say for example, if I'm having a microphone here through which I am recording the voice, so this microphone acts as a system. That means it takes the input as my voice. So my voice here, say x of t, acts as the input to this microphone, whereas the output of this microphone is the electrical activity that you see on the screen or you hear. So the output here, let it be y of t, is the electrical equivalent of my voice signal. So here the mic is acting as a mapping element between the signal, that is the input, and the output. So system can be considered as a device or a set of components that maps two signals, the input and the output. Here the system is the microphone itself. Now a system here, if I draw it in a box, this represents a kind of mapping between the input and output, and we have already seen that the signals themselves are also mappings. So the input signal here is a mapping between the independent variable, that is time here, and the dependent variable, that could be the acoustic pressure. The output signal y of t is also a mapping between the independent variable, that is time, whereas the dependent variable here is the voltage signal or the amplitude of my voice. So a system can be interpreted as an element that maps the input signal that is mapping to another mapping. So it is a mapping between two mappings, you can say. Now, as we have different categories of signal, we do have different types of systems. Let's look at them one by one. A system can be classified into various categories. The first category that we are going to look at is the classification based on the memory. A system is said to be, let me write that. A system is said to be memoryless if the output is dependent on only the current values of the input. So a system is said to be memoryless if it depends the output, the current output value. So I should say if the current output here is dependent on only the current values of the input. If that is the case, then only the system is said to be memoryless. So as in our example here, the output value here, y of t, is dependent on only the current value of the input. So we can represent that as, say, y of t equals to x of t, for example. So in this example, you can see that the current value of the output is dependent on only the current value of the input. Therefore, the system is said to be memoryless. Let's take another example. Let's take an example of, say, your bank account. Say, for example, if you have opened a bank account of type savings, and say you have deposited some amount, say X, in some month, say N. And assume that if the bank offers a rate of interest of, say, 5% if you retain that amount for a month. So we can represent that system as y of n equals to 1 plus 0.05 of x of n minus 1. So what does this mean? The amount that you have deposited in the previous month is x of n minus 1 is getting scaled by the rate of interest, that is 5% of the original one. So this 1 plus 0.05 indicates the rate of interest that you have gained over the amount that you have deposited in the previous month. So the amount that you would get in the current month is dependent on the amount that is being deposited in the previous month. So here you can see that clearly that the current output is dependent on the previous value of the input. So there is a memory involved here. So this system is called as system with memory. So this is an example of system with memory. The previous example that was my voice signal, that is y of t equal to x of t, was a memoryless system. Just because there was no memory element involved, the current output was dependent on only the current values of the input. But in the second example, the amount that was deposited, that is x of n, here we have considered x of n as the amount deposited. So x here indicates the amount deposited, and here the relation indicates that the resultant amount that you would get after a period of, say, 1 month. So this is a system with memory. So this is one type of classification of a system. There are other types of systems also. Second type of systems that we are going to look at is based on what is called as causality. A system is said to be causal. A system is said to be causal if the current output depends on current and or past values of the input, but not on future values of the input. What does that mean? Suppose you have the output, say y of t. So if you are calculating the current output at, say, t equals to t naught, then it must be dependent on only the current or past or the previous values of the input, but not the future values of the input. If it does, then it is not a causal system. Let's take an example. The same example that we have seen, y of t equals to x of t. This system is memoryless, and also this system is causal. In the system classification of memory and memoryless, we have seen that a system is said to be a memoryless system if it depends on only the current values of the input. So all the memoryless systems are said to be causal just because the memoryless system involves only the current values, the dependence on only the current values of the input. So all the memoryless systems, suppose for example y of t equals to x of t is an example of memoryless system, is said to be causal system. Why? Because all the memoryless system are having the output being dependent on only the current values of the input. So all, you can say all memoryless systems are causal. But vice versa is not true. Not all causal systems are memoryless. Okay, but all memoryless systems are causal. Let's take another example. Say for example, y of t equals to x of minus t. Let's take this system. Now, if we look at this system, now we may tend to conclude that this system is a causal system. But let me tell you that this system is not causal. In the first instance, we may say that okay, the current output is dependent on the previous values of the input. Say for example, if t is 2, then y of 2 is dependent on x of minus 2. But we need to take into consideration all the values of t. So both the negative and the positive values must be considered. So if we take the small t as say minus 2, then y of minus 2 is equals to x of minus 2, that is x of plus 2. So here the system is having the current output being dependent on the future values of the input. Such systems are called as non-causal. So this system is non-causal. Why? Because for negative values of t, say y of minus 2 is dependent on x of 2 for t equals to 2. So you may see that the current value of the input is dependent on the future values of the current value of the output is dependent on the future value of the input. If it is, then the system is said to be non-causal. So the most important point to note here is we must check the validity for all t. We shall look more into this in the next module. Thank you.